A wire of length L, area of cross section A is hanging from the fixed support. The length of the wire changes to L1. When mass m is suspended from its free end, the expression for Young's modulus is. Okay. So, basically you have a wire, okay. This has got a cross section area A now and has got a length L originally, and this has been, once it is suspended from a mass m, then this mass is going to apply a force mg Newton into that, right. This force is going to stretch this. So, because of that the length has now become L1, it is a bit more length, okay, and you are supposed to find out the Young's modulus of elasticity for that. So, it is a formula kind of derivation. Young's modulus of elasticity Y is given by stress by strain, okay. Now, what is stress and what is strain? Strain is defined as change in dimensions by original dimension. So, that is here the dimension changing is L, length. So, we can say delta L by L, okay. Now, what is delta L? Final is L1, initial is L, divide by L. So, this is your strain, and stress is kind of pressure, force per unit area. It is a restoring pressure. When you apply a force, the body tries to restore it back, and that force is called as the stress force over there. Force per unit area is defined as the stress over there. So, force per unit area is nothing but, what is the force? Mass mg and area is A. So, just put these values into Y. What do you get? Stress mg by A by L1 minus L by L. So, this will be mg by A into L by L1 minus L. So, this comes out to mgl by A into L1 minus L. mgl by A into L1 minus L. So, your C is the correct answer. Okay, right. Next, two wires are made of the same material and have the same volume. What is being told? Two wires are made of the same material and same volume. The first wire has cross sectional area A and the second wire has cross sectional area 3A. Okay. If the length of the first wire is increased by delta L on applying a force F, how much force is needed to stretch the second wire by the same amount? Okay. So, it is being told is, you have wire 1, you have got wire 2. These are having same volume, same volume. Same volume is very keyword over here. Now, volume is, what is the volume? And they are of the same material. So, it means their modulus of elasticity is same for all of them, same material and same volume. Okay. First wire has cross sectional area A and second wire has cross sectional area 3A, right. Now, remember, if this is A, the length will be L1 and this length will be L2. Why am I writing L1, L2? Why am I writing L? There is nowhere written that the length is same. What is given is volume is same. So, see over here, this is the only trick here. Volume is area into length. Same volume means A1 L1 is A2 L2. Now, A1 is A and length is L1, say L. A into L must be 3A into L2 because the volume is same but the area is 3 times. So, what will be L2? L2 will be A by 3A times L, that is L by 3. Okay. So, if this length is L, then this length will be L by 3. Okay. This is the only trick in this question. Now, you can solve. Okay. So, when you apply a force F, how do you say? Young's modulus of elasticity is F by A by delta L by L, because they are same material. So, both of them should be same, right. So, for us force F by A by delta L by L1 must be equal to F2 into A but instead of A now it will be 3A, sorry, F2 by A by, you want to have the same derivation, same same elongation, so same delta L, and the length is now L2. So what it will be? F into L1 by A into delta L is F2 into L2 by 3A times delta L. Right or wrong? Correct? Now we put in F is the force what we have applied, its length is L, its area is A, and the displacement, I mean the elongation created is delta L. You want to find out F2, what will be that force which will create the same displacement, same elongation delta L, where my area of cross section is now 3A and my length is from original L by 3. Okay. So if you see what will happen, this implies FL by A delta L is equal to F2 into L by 3A into 3 into delta L. Delta L A gone, delta L A gone, L gone. So what do you find? F2 is 3 into 3 into F, that is 9F. It means for second wire F2 is equal to 9F. So it means for the second wire, if you want to create the same elongation, my force should be 9 times of the F. Yeah, you have here 9F. Okay, so the correct answer is 9F. Next, the stress strain curves are drawn for two different materials XY. Okay, there is a material X and there is a material Y. For that, what is drawn is a stress strain curve, right? That is the modulus of elasticity curve. It is observed that ultimate strength point and the fracture points are close to each other. Ultimate strength point and fracture points are close to each other for material X, but are far apart for material Y. We can say that material X and Y are likely to be. We have to choose that. Okay. So let me tell you, when you do the stress strain curve, it will come something like this. Okay. This is your Young's modulus linear portion. Here it is called the ultimate strength, and here you get the fracture point. Okay. So the farther these points are, the more ductile the material will be. You can still stretch it, or you can make the wire out of it, or you can stretch out of it. But if they are closer, it means at the fracture point they will break, the material will break, it will not be further elongated. Okay, this is the basic meaning. It means if the 2 points are closer, then the material is more likely to break the moment you give a force more than its elastic force, right? It's this modulus. This is the point, right? So if it go beyond, it will break, whereas if it is farther, before breaking it will be ductile, it will be elongated. So it means the farther one will be elongated more and the closer one will break more. Breaking is called as fragile. Okay. So if you see, X is closer, so X should be fragile, actually brittle, and Y should be ductile. So A cannot be ductile because it is closer, A can be brittle, B can be ductile, plastics no chance, so B is the answer. X is brittle for you and Y is ductile for you. Okay. Next, when a block of mass M is suspended by a long wire of length L, the length of the wire becomes L plus L. It is elongated by a length L. The elastic potential energy stored in the extended wire. Okay, elastic potential energy stored in the extended wire, right? So there is a straightforward formula: elastic potential energy is half into force. Okay, force into elongation or change in dimension. Half force. How much is the force? suspended by a block of mass m. So, what will be the force? M times G. And what is the change? What is the change? Originally it was L and now it has become L plus L. So, the change is L plus L minus L, that will be half mg L. So, elastic potential energy will be half of m into g into L. Yeah, which L? Elongation portion. So, this one, okay, not this one, B, right. Fine. So, this point what we have done is we have completed the properties of solids. Okay. So, properties of matter is one unit. In that unit you have got properties of solids. Now, you have got properties of liquids and gases, which is also called as properties of fluids. Okay. So, let us take up the next section on properties of fluids.